So we're going to continue. We're going to talk about uniformly distributed sequences, and I only want to say like a little bit about this. A lot of the theorems I'm just going to write because there is the proofs use a good amount of measure theory and some other things, and I'm just going to assume that you guys don't have that, which is okay. It's not going to really like interfere with the main point. So for those of you who've had, a course on measure theory, you can kind of guess as to how some of these are proven. But I just want to start with the idea of a sequence being dense and also the idea of a sequence being uniformly distributed. And there's a very important connection between this and normal numbers and ergodic theory and dynamical systems that we're going to build towards. And so for starters, let's say that S is a subset of R and Xn is a sequence of real numbers. And we say that, so definition is that Xn, and we could call this maybe omega, so let's say omega. Omega is dense in S if for all epsilon greater than 0 there exists lowercase n. So for all S in S and for all epsilon greater than 0 there exists n where the difference between S and x sub n is less than epsilon. So basically every single member of S you can approximate as closely as you want by some member of your sequence. So simple example. Let's look at, say your sequence is given by the following. Let's say 0 over 1, 0 over 2, 1 over 2, 0 over 3, 1 over 3, 2 over 3, 0 over 4, and so on and so on. And S is 0, 1. So I think you can probably pretty easily construct a proof that this is going to be dense. You know that every rational point in S is hit, and then rationals are dense in the irrationals, and it's just kind of a simple exercise. Something more interesting now, and I'll leave this partly as a say homework problem or something. Let's say Xn is equal to the fractional part of n times theta. So this means fractional part. So there's kind of this unfortunate notation that you have both the set braces, it has both the uses for fractional part and set. So here we're referring to fractional part, so fractional part pi is equal to 0.14159 and so on. So we let Xn be given by n times theta, where theta is some real number. And then let's say theorem is that the sequence x sub n is dense in 0, 1, if and only if. Any guesses what condition on theta? If and only if theta does something. Any guesses what?
Not equal to 0.
Well, let's say theta is 1/2, and then you're only going to have two terms in your sequence, 0 and 1/2.
Oh yeah, okay. Irrational?
Irrational? Is that what you said?
I think.
That's the correct guess. If and only if theta is irrational. Sometimes, part of doing real math, and what I mean by real math, I don't mean like you haven't been, but like, let's say like you're doing research, is getting the right theorem you want to state, right? That you have like an idea something's going on and you have to kind of poke around and see, okay, is this, what's really happening? Is it this? Well, no, we tried this, that doesn't work. There's some sort of condition, no, maybe it's irrational, let's try to prove that. And so I'll give this as an exercise, but there's kind of visually what's really going on here. So you think of this interval 0, 1. Let's just take half open. This will be a little easier for what I'm going to do. And imagine if you take these two sides and put them together and you draw it like it's a circle. So you basically have something kind of like you fold it like this. And let's say this is a unit circle. So what you're really doing is you're rotating by some angle. And it's not going to be theta exactly. I guess that's theta over 2 pi theta, I guess. Yeah, because you go from 0 to 1. So your angle, in this case, you do a rotation by 2 pi theta. And then you look what's here. And then you do another one you have, let's say, another 2 pi theta rotation. And so on and so on. So what you're really doing is essentially you're rotating along the circumference of a circle. And you're saying, okay, well, if we do a rotation, if it's something like a 90-degree rotation, then you're just going to be spinning around and there's only going to be like 4 points, for example. So my claim is that if theta is a rational number, then actually the sequence is periodic. And that's very easy to prove. So everyone can try doing that as an exercise. But has anyone who's still a student, has anyone seen this question before? It's possible you saw this in a class. Maybe not. So then it's a new question. It's harder than it looks. It's not that hard, but it's...
I just remember it's for me very similar to... I'm not familiar with term to numbers that are not Rozmiernie.
Rationally independent, I don't know.
Yeah, something, like that we can't take one n times the other m times and they will be equal.
Okay, so it's a type of linear independence. Yeah.
And so you can prove that you can, by multiplying by natural number, by some whole number first, your element, and the second, you can make any small number if you want.
That's a very good start to proving this. So see what happens, combine it with the pigeonhole principle. So yeah, so good idea to start with. And so you've maybe seen something related to this in some form. So yeah, see how small you can make something like this, and yeah. So so this is a first result here. So density is, this is a condition that comes up a lot. This is going to correspond to something with normal numbers as well that we're going to mention. But those are just a couple, let's say simple examples. This one's really easy to prove, and here you can do something kind of like he suggested. And we want to deal with a stronger condition called being uniformly distributed mod 1. And this is something that I want to say is very Austrian. So if you go specifically to the country of Austria, you run into many people that care a lot about this. So math can be very regional. There can be certain places, certain things are dealt with more. And there's a historical reason for this involving Austria, but I can kind of tell the story if anyone wants, but I want to give the following definition. So definition is that a sequence xn is uniformly distributed mod 1 and I am going to always abbreviate this UD mod 1. If for all intervals, say I subset of 0, 1, the limit as n goes to infinity of the number of elements of, let's say, 1 less than or equal to m less than or equal to n, such that the fractional part of x sub m is in I divided by n is equal to, and there's a reason I'm going to put this lambda for Lebesgue measure, and I'll just kind of say, for those who don't know what Lebesgue measure is, this is just called as the length. And the reason I'm putting Lebesgue measure there is because later when we talk about some other things, we're going to want to replace this by another measure. So basically, what is this saying? It's saying, for example, if I is the interval 0, 1/2, then you can kind of very intuitively, informally think of this as like there is a 50% chance that your fractional parts are going to be between 1/2 and 1. If I is 1/2 to 2/3, there'd be like a 1 in 6 chance that your fractional parts hit that, and so on and so on. So it's essentially saying that your fractional parts are, let's say, uniformly distributed, as the name suggests. And so we're just writing it this way in terms of we count the number of times that the fractional part hits the interval I. And I want to remark that we're quantifying over, I say intervals, so well, what does that mean? That means open, closed, half left closed, right open, and so on and so on. With every single real endpoint, you can define it like this. But there are many weakenings that are equivalent. So for example, if you only want to look at open intervals with rational endpoints, it's not too difficult to prove that it's sufficient to only check on those intervals. So, note, it is okay to only check on, say, to check with intervals with rational endpoints. But it doesn't just have to be rational. There can be like only with endpoints that have that are rational numbers with powers of 2 in the denominator, for example. That's also fine. So you don't need to check on every possible thing necessarily. So does this definition make sense? I'm going to give a bunch of examples.
M, it's a digit of?
There's no digits, it's a member of the sequence. So we have a sequence.
Okay.
So we're saying how many times does the fractional part of that sequence hit the interval I? Definition clear to everybody? If not, please ask, because we're going to do a bunch of stuff with it. And each one of the remaining talks from now on is going to care about this definition. So let's give some examples. And we're actually going to start with the same first 2 examples as before, except it's a bit harder now to prove this. So examples: 0 over 1, 0 over 2, 1 over 2, 0 over 3, 1 over 3, 2 over 3, and so on, is uniformly distributed mod 1. Let's say that's exercise. And this is kind of similar in some ways to doing the Champernowne number proof, but it's easier. But I would recommend anyone just kind of, this is one of these things where you get your hands dirty, like you need to just kind of go in and directly check with the definition because, you're given some interval I, let's say I is AB, something like this. And you need to check, like, let's say you count out to like some position N. So if you're given you're given N, so you have like, 0 over 1, 0 over 2, 1 over 2, and so on and so on. And let's say you have 1 over, I don't know what we want to call it. Like it's going to be, 0 over maybe f of n, 1 over f of n, and so on. And then maybe you have some sort of like term t over f of n. It's going to be a t of n, of course. So you basically stop right here. So this is position n. And so you have like a few things like this is some grouping that's completed, this is one that's completed. There's also the ones like 0 over 3, 1 over 3, 2 over 3. This one's been completed. But then if you pick an arbitrary position, well, you may not be finished with what you're doing, right? So remember, you can't just check along the subsequence. And so you need to say, okay, well, you have some interval I. You estimate for each of these how many times you see them by the end. But here, you're starting something but not finishing it. So what's the estimate and, what type of over or under estimates can you do that don't affect kind of your running total so far, and you got to make sure it puts together in the right type of way. It turns out that actually if these blocks are like too long, and we'll see this in a minute, then you don't get uniform distribution. So if we were to like extend these, too much, because we actually end up getting a problem that the limit doesn't exist. So keep that in mind as well, that it's not just if things look like they're kind of doing some nice stuff here. If you don't do it in the right sort of way, that the limit is going to, you're not going to have lim sup and lim if be different or the same, then it's not going to exist. So like you could do something like this. You could do something like 0 over 1, and let's say you have 10 to the 10 to the 1 of these. And then let's say you say 0 over 2, and then let's say you have 10 to the 10 to the 2 of these. And then 1 over 2, and you have 10 to the 10 to the 2 of these. And then you have 0 over 3, and then you have 10 to the 10 to the 3 of these. And you have a 1 over 3, and then you have 10 to the 10 to the 3 of these, and so on. So you look at a sequence like this, and if you were to check this expression for being uniformly distributed at the end of each of these, it's going to look like it's going to be a uniformly distributed sequence, but the limit doesn't exist because whatever's going on here is completely dominating what happened before. So like these zeros, like the number of these zeros, for example, completely screws everything up because you put down so many that it overwhelms whatever was kind of the good stuff going on before. And then it's kind of down to where it should be by the end, so you get a difference between the lim nth and the lim sup. So this is something to be very careful about. But if you just do it like this, you have to be very, very careful. I would very strongly recommend everyone, write out the limits, just go everything by the definition of it, make sure that you're not cheating in any sort of way, and that's because a lot of these problems are just very delicate in this sort of way. Even if some number seems like it's a normal number or some sequence seems to be uniformly distributed, you can run into all kinds of problems if you put things together in a maybe not totally careful type of way. So just be careful. So I would recommend everyone try this one. Like any student I have that wants to work with me, this is one of the first things I give them just as a practice to get started. Okay, let's do another one. And the sequence, so example, n times theta is uniformly distributed mod 1 if and only if theta is irrational. So it's not just dense, it's uniformly distributed as well. Whenever it's dense. If it's periodic, of course, it's not uniformly distributed. What about the following example? Log of n. And of course we mean from like 1 to infinity. I'm not writing that, but do you guys think that a log of n is uniformly distributed mod 1? Any guesses? What do you think? It's okay to be wrong.
It looks like, yes. It has to be. I would bet on it being uniformly distributed.
Yeah. What about your thoughts?
I think it will be too slow and it will not have the concrete limit.
So what happens basically is it should be uniformly distributed, and if you make it grow just like a tiny, tiny little bit quicker, it is. But it fails to be uniformly distributed for the same reason that this fails to be uniformly distributed, and it's just a really subtle boundary right here. So that's where I think this is a really good example, because this kind of looks like an artificial construction here, but log n is a pretty natural function to come up with. And so I forget exactly how much, I think I have to double check this. Maybe if you multiply by log n or something and then it becomes uniformly distributed, you just need a little extra kick and it works. So it's just like right there. All right. And so another fun one. This is, let's P of x equal, let's say, a times mx to the m plus plus a1x plus a naught be a polynomial. Then sequence P of n is ud mod 1 if there exists j where a sub j is irrational. So that's interesting. I can actually give this, if I give you guys a certain theorem, I could give this as an exercise to try to work out. I was thinking of doing it actually here, but there's a little bit it's a little too involved and there's too much I want to talk about, but I can write down a relevant theorem, so I want to give some theorems on checking uniform distribution, because something like this, if you just go directly from the definition, it's too hard. I think just even n squared alpha was something that was a bit too difficult for anyone to do until certain nice theorems were proven. So this is an example. And let me write down a couple conditions that are equivalent to being uniformly distributed mod 1 and are useful. Are there any questions so far? So theorem, and I'm going to give like a little hint as to how to prove this, this one and the next one. I'm not going to say exactly. But xn is uniformly distributed mod 1, if and only if, for all f in C of 0, 1. So for those who haven't seen this notation, this is continuous real valued functions on 0, 1. We have that the limit as n goes to infinity of 1 over n sum from n equals 1 to n of f of the fractional part of x sub n is equal to the integral from 0 to 1 of f of x dx. So anyone have a guess at what the intuition as to why this is true might be? There's a bunch of technical stuff in the proof that, I mean, you can work out, but there's like kind of a basic intuition here. Because it looks, you know, not like what I wrote. Roman, do you know?
Like ergodic theorem.
Oh, it absolutely does look like that, yeah. It's one of the reasons I wanted to write it. So basically what's going on here is, you have, if you, let's say you're given some interval, I subset 0, 1, and you can write, say like, I have I sub I, let's maybe 1 sub I, say an indicator function. So we could say like 1 sub I of x is equal to 0 if x is not a member of I, and 1 if x is a member of I. And so you can check that testing with these functions is equivalent to checking if you're uniformly distributed mod 1. You just add up how many times x sub n hits is, you know, going to be 1 when you evaluate it with this function. And basically the idea is you do some approximation argument with continuous functions with indicator functions. So it's this type of thing from analysis where you approximate some function with another class of functions. If you know what I'm referring to, you can fill in the details. If not, then just don't worry about it and just think that theorem is true. So it basically comes down to an approximation argument that you're really just checking for all intervals. By doing this, you're effectively checking on all intervals, and then the other direction's not too hard. You could approximate indicator functions as closely as you want. So if you're given a particular interval I, you know, let's say you have some interval I, and if you want to make, like, let's say it's right here. So this is I. Let's say this is 0 to 1. And okay, let's say you want to count how many times your sequence hits the interval I. Well, what you really do is you say, let's look at this function. Let's say 1 sub I. Okay, it's not a continuous function, but you can approximate it by continuous functions really easily, right? You can go kind of like this. Maybe this is like some epsilon distance right here. And just approximate it closer and closer, and then you'll get to know what happens for that interval. Okay. Does that just kind of intuition make sense as to what's going on here? Okay. So what to me is more useful and more interesting is the following thing called the Weil criterion. So the theorem that's most often used, I mean this is also used for a lot of things as well. So, but the kind of easily applicable, well, not easily, but let's say more easily applicable, because a lot of the stuff is actually very hard in the details. So this is called the Weil criterion. And what this says is that xn is uniformly distributed mod 1 if and only if for all non-zero integers h, we get that the limit as n goes to infinity of 1 over n sum from n equals 1 to infinity of e to the 2 pi I h x sub n is equal to 0. So that's something you could hypothetically check, right? So just as a reminder that e to the I theta is cosine theta plus I sine theta. So your problem on uniform distribution ends up becoming, with estimates involving trig functions. That doesn't mean it's easy. That can be very, very, very difficult, but you can reformulate a lot of things like this. And a very significant portion of results in uniform distribution, or even dealing with specific sequences, use this criterion or some sort of a corollary of the criterion. Why is this true? Well, it basically follows from this. You can do another approximation argument. But you can imagine there's all kinds of Fourier, this and that you can do, and it's so a lot of results. There's a whole big group of people who deal with estimates involving these sorts of exponential sums or trigonometric whatever. And I don't know this stuff that well, but you know more about uniform distribution the more you know about that type of stuff because of something like the Weil criterion. And I'll give a corollary of this. There's something called van der Korpit's difference theorem, and you can try to prove this using the Weil theorem. And van der Korpit's difference theorem is what's going to give us this thing about the polynomials. So theorem, and this, I'm just really giving like a couple select things here because there is so much material. There's just a crazy amount of material developed to determine if this sequence is uniformly distributed or if this one isn't. So this is van der Korpit's difference theorem.
Okay.
Is there a question?
Some guys do not understand in terminology IFF. IFX.
If and only if, okay.
Okay, yeah. Let me write that to be clear. This is if and only if. Or in other words, you have everything. Any other questions? I want to make sure, even if it's something simple, please ask. So you can try proving this as a, this is a corollary. Say this follows from the Weil criterion. Let xn be a sequence of real numbers. So if for all positive integers h, we have the following the sequence x n plus h minus xn, from say n equals 1 to infinity, is uniformly distributed mod 1, then xn is uniformly distributed mod 1. So you can kind of imagine that there could be some way to bring in this, you have to work out the details, but you have a lot of even kind of a similar, in this you're only quantifying over positive h, but when you're taking a look at the difference of these, you can plug in n plus h into here, and there's all kinds of things you can do with exponent rules and estimates and things. So I would say take this as an exercise to attempt to prove this. And I'll give a reference as well, because you can find all this stuff. There's a very easy to get book where you can find all these things. Okay, so van der Korpit's difference theorem. So how does that apply? To this thing right here. So you can do it's a bit of work to do, but you can do something like a proof by induction for this. So we do have a bit of a base case that we know that n theta is uniformly distributed mod 1 if and only if theta is irrational. So when you take differences of polynomials, right, if you had something like p of n plus h minus p of n, it's something kind of like a derivative, and you lose 1 power in a term. So this is a very useful type of thing where you can kind of do something like a differentiation to simplify the problem. So I'll suggest you guys, try to do this on your own. Like I said, it's not like quite immediate. There's still some stuff that needs to be done, but it is basically a proof by induction. So any questions so far? Okay. So I wanted to mention a very nice theorem, and I was actually going to prove this, but I was just digging into it too much, and there's once again, there's too much measure theory. There's Fatou's lemma we need to do and a few other things, but I'll write this over here. And we're going to be using this theorem as well in future lectures. So theorem. Suppose that AN is a sequence of distinct integers. Then the set of x such that AN times x is uniformly distributed mod 1 has full measure. So remember this concept from the last lecture that we talked about being measure 0 or full measure. So in other words, it's full measure if the complement has measure 0, or you can think, your probability of if you pick x uniformly at random, then the probability is 1 that AN times x is uniformly distributed mod 1. And this is actually going to be a way that we're going to use this to prove that the set of normal numbers in base B has full measure. And just so everybody knows, if you intersect countably many full measure sets, you get a set that's full measure. So this is a nice thing that, probably you could actually just prove that based on the definition of zero measure. I was thinking like using a bigger measure theory apparatus, but probably that special case you can prove without knowing that much. So maybe take that as an exercise too if you're curious. So I want to give the big theorem, and this is due to Wall in 1949. And there can be funny things sometimes with normal numbers that sometimes like the most powerful things can be incredibly easy to prove. And sometimes stuff that's like a very specific question that doesn't have any application outside of that interesting question can be incredibly difficult. And this is an example I would, if anything, if I were to name this, I would call this the fundamental theorem of normal numbers. But it's very, very, very easy to prove. And this is in Wall's PhD thesis at University of California, Berkeley from 1949. And this is a thesis that's cited in many, many, many papers, but guess how many people have actually read the thesis that they've cited? I don't know the number, but it's almost nobody. So I actually got a hold of this thesis. So there's two PhD theses I did this for. And, this is in 1949. It's in this microfilm format. So this is when I was a postdoc at University of North Texas. I actually contacted the library at University of California, Berkeley. I got them to mail me this microfilm. And then I went and then page by page, I copied it and scanned it into a file. And so now I have this and I've sent it to several people so they can read it, but it's not something you can just look up on MathSciNet or get an article or something and download it. You needed to actually contact the library. So this is somewhere on some old hard drive, I think. I do have it. I know I sent it to some people who probably have it more organized than me. But there's several things he proved that were of interest. And so what he proved is that, theorem that x is normal in base B if and only if the sequence b to the n x is uniformly distributed mod 1. And there were a lot of people, I think, there were even very strong mathematicians, including Erdős, Copeland, Sierpinski, and I think several others that somehow just kind of assumed this result without proving it for many, many years. This wasn't actually written down, until 1949. There are a lot of little kind of subtle things that people assume about normal numbers that turn out to be not so simple. And I can maybe talk about some of these later, depending on time. But why is this true? I'll leave this also as an exercise to prove. Basically, what happens, we have this algorithm for generating the base B expansion. T sub bx is bx mod 1. Right, so this looks like the following. You have, it goes like this, and then it's like this. You have some interval here, another here, and then dun, 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 and then you have a last one. So this is like 0 over b, 1 over b, and so on, up to b minus 1 over b and b over b. And Right, so this corresponds to the digit 0, the digit 1, and the digit b minus 1. So, you know, what you're basically doing, like I mentioned before with a binary expansion, is that you track where your real number x goes. You apply t sub b to it, and see where you land, then you apply t sub b to it again, see where you land again, and so on and so on. And so when you're looking, for example, okay, how many times does the digit 1 show up? Well, that's corresponding to this interval here, 1 over b to 2 over b. So if you just want to count the number of times 1 shows up, that's kind of like counting how many times the sequence b to the nx hits this interval right here. If you want to count how many times a block of length 5 shows up, well, there's going to be some much smaller interval of length 1 over b to the 5th that you can also track. And, well, to be uniformly distributed mod 1, you have to hit that the right amount of times. Just like that block of digits, you have to hit the right amount of times to be normal. And you need to say, okay, is it okay just to check uniform distribution on intervals who have, that are rational numbers with denominators that are powers of b? It's a not very difficult approximation argument, but basically this is why it's true. Like there's just, like I said, just kind of details to fill in. It's good to actually write those details for practice. But all of a sudden, this brings in a lot of very powerful machinery that didn't exist before. That normality is equivalent to being uniformly distributed and the sequence being uniformly distributed. And I even mentioned like this Weil criterion involving exponential sums. So I didn't mention, one of the ways that people do prove specific numbers are normal is in some ways turning it to a problem in uniform distribution and using like all these sorts of big high-tech estimates of exponential sums. That's not a technique I use as often, but I know some people who are very proficient in that technique. So this is really powerful, and I wanted to, I forgot to mention this earlier. Let me give also another, okay, good. So I wanted to, there are a couple things I prepared specifically for you that we'll get to. So I wanted to remark as well that there's a couple things that are unknown, like for example, is the sequence 3/2 to the n? Is this uniformly distributed mod 1? See, that kind of seems like it's a simple problem, right? But, I mean, we already know that the following one I'm going to write is a problem for the next millennium. So say 10 to the n times pi. So this is equivalent to pi being normal, and this is, And even further, not just is this, so what about, okay, so uniform distribution is giving you this notion, giving you normality, but what about a sequence being dense? What do you think that gives you? So if b to the nx gives you, being uniformly distributed, it gives you normality on base b. What about b to the nx being dense? What does that give you? So b to the nx is dense is equivalent to what condition? Something easier than being normal.
It's not rational?
No. It's
I should try.
Yeah. So let's so here, for example, let's say x is the sum of 1 over, no, it's good to try, it's good to be wrong, because then you learn, right? Because then you get an example, you think, okay, say something wrong, and then, okay, where does that fail? Here we go. So what about something like this? You take something here, there's a whole bunch, there's a 0 and a whole bunch, there's a, sorry.
Nothing can be answered.
I mean, about what? What do you mean?
Any answer will be false.
Oh, there's a true answer. So there's a simple form. So with this one right here, so this is not going to be dense when you 10 to the n, right? 10 to the n times x is not dense, but this is irrational. You can check that this is not going to be dense. So like, for example, it never gets too close to 1. Right, so anytime 10 to the n x, this is always going to be strictly less than 2 over 10. So there's another condition. It's not about irrationality, it's about something else.
You can construct 10 base normal for which, not normal, for which the frequency of 0 should be 0 or should be 1, and the sequence will be dense in the unit interval.
Oh, for sure, for sure. Yeah, absolutely. But what's the condition? So there's a very simple condition that this is equivalent to. And then we'll give an example like you were suggesting. So this is equivalent to, so let's say X is, Jan Bajot calls this rich, which means that every block of digit occurs at least once. Every block of digits occurs at least once. So can everyone kind of see why that's the case? And so this is strictly weaker than being normal. Because you say you could do something like, let's say you did a number like 0, 0, 0. Okay, let's say there's 10 to the 1 of these. And then you do, let's say, 1, 2, 3, blah, 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 up to 9. So there's only going to be 9 of those. Let's say we have a bunch of zeros. We have 10 to the 10 to the 2 of these. And then you go 1, 2, 3, 9, and then we go 10 up to 99, something like this. And then you do, like, say, 0, 0, and this is going to be like 10 to the 10 cubed, and so on. Okay, so this is, oh wait, we want dense. Yeah, so this
is dense.
This is dense, yep. But it's not normal. So,
maybe a simpler example is fractional part of log n.
yeah, fractional part of log n, that would be
Which is dense,
yeah.
but not uniform.
Yeah, true, yeah, this works, yeah. Good point. So any questions so far? Okay, so let me see where we are. We have, okay, we got to move a little quickly. I'm not going to get to discrepancy.
Sorry, can you repeat what do you mean by x equal? I can't fully understand what is next.
So x, right up here?
No, one year.
Oh, the sum from n.
It's sum, okay.
Yes.
I'm sorry, understood.
Yeah. So this is a well-known transcendental number.
Louisville. Yeah, Louisville. No.
Yeah. But so yeah, you can cook up, there's all kinds of things you can cook up, or you can make the sequences in different ways. So I want to move a little, we don't have like too much time yet, so there's one thing I definitely wanted to get to and promised about rational addition preserving normality. So we want to look once again. Let's say S is the set of all real numbers y, and I want to address a comment on this from the last lecture, such that for all x normal in base b, x plus y is normal in base b. And there was a comment, and let's see. So we don't need to worry about negative numbers or not. I was just kind of thinking again afterwards, because normal plus normal is not normal necessarily. So it doesn't really actually end up being a problem, because you could take, like, for example, if you have like x is Champernowne, then I'm pretty sure that something like, I don't know, say base 10, then if you were to have something like 1/2 minus x should also be normal in base 10. I mean, I need to fill in the details. But nonetheless, x plus 1/2 minus x is going to be 1/2, which is not normal. So generally, we don't expect, the set of normal numbers is not going to be closed under addition, right? So we need something that's, in fact, what this is, what you're suggesting is basically an argument that there are no normal numbers that preserve normality under addition. So it's an entirely different set. And my claim is, like, theorem is going to be that the set of rational numbers are a subset of S. So rational addition. And I want to give a couple another theorem we're going to use about normal numbers, and then I'm going to prove this using uniformly distributed sequences. So this is something like it's possible, you could say, okay, well, you take a rational number and maybe think what this grade school addition algorithm is going to do, and it's probably going to be very painful. There's probably a way to prove this theorem using that. I've never seen it, so I wouldn't want to do it because there's a much better way of doing it using the machinery here. But I mean, rational addition is pretty simple, right? It's every rational number is eventually periodic in base B, but there's a better thing to do. So let me, I'll prove this in a little bit, but first theorem, and this is more difficult than it looks, but this is important. That x, if x is, let's say, x being normal in base P is equivalent to x normal in base Q. This statement here, and that's if and only if log P over log Q is rational. So let me just clarify what this condition means. It's like comparing, for example, like 100 and 1,000. Okay, log 100 over log 1,000 is rational, right? You raise 100 to the 3/2 power to get 1,000. But, so write log of 100 over log of 1,000. That's like 2/3, right? So being normal in base 100 is equivalent to being base normal in base, being normal in base 1,000. Let me just emphasize that this is not obvious even though it looks that it is.
More or less, who is the author of this result?
Schmidt. So the full version, there's weaker versions that are known earlier, but we do Wolfgang Schmidt.
The same who names after Schmidt's name again.
Oh yes, he did many, many things. Yeah, he's a very, very strong and important number theorist in other places far away as well. So basic, getting examples of numbers that are say normal in base 10 but not normal in base 2 or showing existence. This requires some more work. So there's the weaker versions of the theorem. I forget who they're due to. Maybe some are Niven and Zuckerman. I honestly don't remember. But we know that, for example, a weaker version would be theorem that being normal in base B is equivalent to being normal in base B to the K. I mean, this is really all we're going to need for this. And a lot of this is dealing with what happens with arithmetic progressions. So there's a reason it's actually not quite so simple, because when you're talking about being normal in base B to the K and comparing it to here, what you're really doing is you're checking blocks along positions that are congruent to 1 mod K, and you're claiming that that's enough information, and that's not really so clear that it is. So if you try to actually write out a proof for this, it's some work. So it's one of these theorems that says, oh yeah, of course, base 100 and base 1,000 are the same thing, or base 10 and base 1,000 are like the same, but it's really not so simple. But we're going to assume that theorem, and so let's do the following. So this will be a little bit of a theorem hopping, but okay, let's say that we have, so suppose that x is normal in base B, and that q is equal to, let's say, alpha over beta is rational. So we know that the sequence b to the n x is uniformly distributed mod 1, right, because x is normal in base B. So let's consider the sequence b to the n times x plus alpha over beta. Okay, so we want to show that this is uniformly distributed, but we need to be a little careful. Okay, so let's look at. So we want to look at this sequence, and so what I'm going to do is this is equal to b to the n x plus b to the n times alpha over beta. Okay. All right. So the problem is that this sequence here, this is periodic, right? And if you add a periodic sequence to, we know that this is uniformly distributed, and this is periodic, but there's a little bit of a problem here that like what happens when we add a periodic sequence to a uniformly distributed sequence, and it may not be uniformly distributed. So let me give an example. So let's say we did something like the following. Remember this example, 0 over 1. Let's just do it like this, 0 over 2.
Is this equality?
So this sequence is equal to this sequence. So what I'm saying is if we show that this sequence is uniformly distributed mod 1, then we show that x plus q, or x plus, say, alpha over beta is also normal. So to show that rational addition preserves normality, it would be enough to show that this sequence, which is equal to this, is uniformly distributed mod 1. I'm going to argue right now that we can't make this conclusion too easily. So there's a trick we can do to get around it. Because this is periodic, right? This sequence here, this is periodic. You know, we're always talking mod 1, just to be clear. So we're always talking about fractional parts.
Maybe equality not in the classical sense.
What do you mean?
I mean, distribution of these sequences will be the same.
Well, here I just use the distributive law.
Okay.
Right, so the b to the n is plus. So anyways, this is periodic, and like we know that this part here, this is UD mod 1. But what I'm going to show now, just to illustrate that adding a periodic sequence to a uniformly distributed sequence does not preserve uniform distribution. We may get something back that's not uniformly distributed, and I'll give an example. Let's say we have the following sequence, and you can check that this is uniformly distributed. We're going to go 0 over 4, let's say 2 over 4, 1 over 4, 3 over 4, and then we're going to go 0 over 6, and then 3 over 6, 1 over 6, 4 over 6, 2 over 6, and 5 over 6, and so on. So what we're doing is we're making it so all the odd locations are less than 1/2, and all the even locations you have a term that's greater than or equal to 1/2. And you can check, it's not too difficult of a computation based on the earlier exercise. This is uniformly distributed mod 1. That's not too hard to show. But let's say that you had a periodic sequence. Let's say we had something like 1/2, 0, 1/2, 0. So this is periodic. And what happens when we add these two sequences together? So we have a uniformly distributed sequence and we have a periodic sequence. And when you add these together, what do we get? We get 1/2, 1/2. Let me think. We need to do it slightly. We need to do it like so 1/2. I'm trying to make this force to be on one side of this. This one here needs to be. If we go. Oh yeah. Sorry. It's 1/2, so it's 2/4. Then 2/4, and then this one becomes 3/4, and then 3/4, and so on. These are all greater than or equal to 1/2. So when you add this periodic sequence to this uniformly distributed sequence, you get a new sequence where all the terms are greater than 1/2. So greater than or equal to 1/2. So you never hit anything in the left side of the interval. So this is where we need to be very careful. This is a wrong assumption that we have something here that's really simple. So if you add that to the original sequence, surely it must be uniformly distributed, but definitely not. So we need to be a little more careful. So what we do, how do we get around that? There's a little trick. So does everyone see why we can't just finish?
Can I come again, this mind?
Sorry, what?
I don't understand this mind.
Okay, uniformly distributed sequence,
Yes.
right? Periodic sequence. You add the two together and you get a sequence that all the terms are at least 1/2.
I altered on 2. First with 2, first with 4.
So 1/2, right? This is 1/2, then this stays the same, and then 1/4 plus 1/2 is 2/4.
Okay.
2/4 plus 0. I made the mistake of not getting the common denominator at first. That's what I was stumbling around. But it just, everything. You add some term, you're adding 1/2 to every term that's between 0 and 1/2. So it moves you up to the right side of the interval. And the stuff that's already on the right side of the interval, you're adding 0, so it stays on the right side of the interval. So this new term here, every term is greater than or equal to 1/2, so this sequence is not going to be uniformly distributed. So we have to be very careful what we add. I know the time is running. So what do? So the trick is as follows. So we so suppose that the sequence b to the n alpha over beta has period m. So it has some period. We don't know what it is. We could figure it out, whatever. It's m. So rather than showing that we have a sequence that's normal the sequence here is uniformly distributed to show it's normal in base b, let's actually show that this is that a subsequence of this is normal in base b to the n. So instead, let's consider, so we show that x plus alpha over beta is normal in base b to the m. This is what we're going to show. Instead of showing it's normal in base b, we're going to show it's normal in base b to the m, but we know that being normal in base b to the m is equivalent to being normal in base b. So what we do then is we say, okay, let's look at the sequence b to the m to the nth power times x plus alpha over beta. And then when we distribute this, we get b to the m to the nx plus b to the mn alpha over beta. But since this was m periodic, this is just a constant. Okay, so we're just adding a constant to a uniformly distributed sequence, right? This is uniformly distributed mod 1 here, because, and that's because x is base b normal, implies that x is base b to the m normal. Right, so we get this is uniformly distributed, that's a constant. It's easy to check if you add a constant to a uniformly distributed sequence, you still have a uniformly distributed sequence. Right, so that altogether implies then that x plus alpha over beta is base b to the m normal. Which then implies that x plus alpha over beta is base b normal. Okay. So does this answer?
Actually, answer another question. So if you shift a normal number on a rational shift, it is easy that you have non-normal number.
No, what do you mean by shift? We're talking about addition.
Plus rational number.
So
since any rational number is periodic in any expansion, so you will shift the frequency to another
Well, it's going to be normal. That's the theorem, is that it will be normal. So anytime you add a rational number to a normal number, you get a normal number. That's what I just proved. I can go over the sketch again if it's...
So if you have a normal number and plus a rational number,
Yes.
your answer, you will have also normal number.
Yes. That's what this
I
proves.
don't believe.
So is there a mistake?
Having, maybe it's just my illusion. So if you shift specific number, shift the frequency of specific number. For instance, if you plus 0.5555555 in decimal expansion.
Yes.
So actually, I mean simply normality, not normality.
Oh, yeah, it was simple. Yeah.
So my counterexample failed, so sorry.
So if we're talking, okay, simple normality means that every digit occurs as often as it should. So is simple normality preserved by rational addition? Probably not, and that's what
Yes.
I can believe that claim. Is normality preserved under rational addition? Yes, and it's the best way of doing it is using this machinery with uniformly distributed sequences. And could you do this by looking at the addition algorithm? Probably, but I think no one in their right mind would choose to do that instead of just doing this. Yeah, no problem, no problem. And you can also show that non-zero rational multiplication preserves normality. That's more difficult to show. I don't think I have time to write down any, yeah, we're already a few minutes over. So that's in Kuiper's and Niederreiter. So let me just write down the reference to a good reference for uniform distribution. And because the spelling of this name, I always screw up. So the title of this book, and you, by the way, you can also just Google this, and one of the first matches, there's a guy at a University of New South Wales that just posted the PDF on his website. So you can just download it. It used to be a Dover book. I would tell everyone to buy it because it's a cheap Dover book, but it's out of print. So it's a uniform distribution of sequences. And there's a lot that I wanted to talk about, but we didn't get to today, unfortunately, but that's fine, of sequences. And the authors are, so this one's easy, like Kuiper's or Kuiper's. And then this is the one that gives me some trouble, Niederreiter, E-R-R-E-I-T-E-R. So you can find the answers to many of the questions I posed as exercises if you want here. So. Okay, so I guess we have to call it a day for now because it's a few minutes past.